Thank you for the invitation. So I came to this conference to present mostly some recent work we did that I will present tomorrow. But he asked me if I can talk a little bit about the work we did with FIRETEC, which is a physics-based model that some of you might know, but some might not know. So, and because I was in the PhD jury of Aurélien, and there is the starting work of William, I decided that it was interesting to present this material about the way to model wind vegetation and how Jean-Luc, my colleague from INRAE, tried to evaluate the code against FireFlux a long time ago. And as Craig knows, he has never done this work in a paper, unfortunately, but still interesting to look at that. So FIRETEC is a physics-based model that solves the atmospheric flow dynamics. So the scale are finer than what we saw just before. You use a compressible code and time steps splitting. But there is a combustion model, so there is a slightly more physics in the way to resolve the fine scale. And there is an explicit role of vegetation. We don't use a sub-model like the Balbi or Rödermel. But on the other hand, as you will see, there are some limitations to go to very large scale. So there has been some previous attempt to do evaluation of the model and many applications regarding topography, interaction with beetles and fuel treatment. I think there are something more than 50 papers in the Web of Science referred to FIRETEC. So as I said, here I will focus on the way to simulate a wind flow over a tree canopy, especially in the context of the starting PhD of William, and about the prediction that we had on FireFlux. So just an animation, because every modeler wants to show his animation. So this is FIRETEC, basic simulation in Aleppo pine forest. So the grid is 2 meters, and so it allows to resolve the heterogeneity of the fuel at this scale. And you can see that some of the trees will burn, some will not. You have some details of the flame, and the plume is represented by a depletion of oxygen. We track the plume. So here we have a simulation with a given condition. So such a model can be used to understand the different factors of the propagation. So if I take a snapshot 5 minutes after in fact the simulation starts earlier than that on the left, but there is just a cut to this part. And so 5 minutes after the ignition, if you change the wind speed, you have twice as big wind speed, then you will see that the plume is more tilted. The flame will be longer and more tilted too, and the spread rate is higher. You can change the moisture condition, so this is typically for a dry summer condition. And for the same wind as in the beginning, you see that the fire is about the same velocity, same spread rate as when we double the wind speed, which means that there is a significant impact of these conditions. The plume is more vertical, the flames are higher, and the trees are also more yellow, just to represent the moisture effect. And on this last one, you can see the slope effect, because the fire is more narrow and the plume is tilted. So we choose the number more or less so that they provide the same impact on the spread rate, just to give an idea. Some example of the studies that has been done. As I said, there are many, but we worked in the past on the impact of fuel treatments. In France, there is this legal obligation to do some clearing around houses, and the legal distance is 50 meters. It was estimated coarsely from radiation a long time ago. And so we decided to use the model to simulate the thermal solicitation to virtual sources at 10, 30, and 50 meters. And we compared the average temperature during 1 minute and maximum fluxes during 1 minute, average during 1 minute, to compare them to some thresholds that are used by operational people to know if they can go. And what we found was that in some cases, especially when there is some slope, 30 meters was not enough, especially for the radiation. And also for the threshold for the temperature, which was 90 degrees. A study that was led by Caroline Sieg from US Forest Service, because you can change the fuel moisture and this location, you can look at the impact of natural disturbances such as drought or bark beetles. So here it's bark beetles. Some of the trees are attacked, and so the moisture is much lower in some trees. And we can see then and study ecological application to know if there is synergy, antagonism, or independence between the two disturbances. So these are just two examples. So going back to the FireFlux experiment, our domain is smaller than what can be done with WRF S-Fire or with Meso-NH Blaze because the computational costs are much higher. Typically, we use the 2-meter grid, as I said, so this is already a big domain for us, even if we can do bigger than that with the big machine of the Lanel. Here the vegetation is explicitly accounted for, the tree canopy, which is why I present this material, because we investigated a little bit the effect of this tree canopy. And it's also an opportunity to detail how wind flow are simulated to compute precursor wind flow to initialize the simulation with the right amount of turbulence. So typically there are these two steps. First, we compute some precursor wind flows using cyclic boundary conditions to generate the right amount of turbulence that needs times and distance to set up. And we specify the target wind at the highest value at the top of the tower. And once we have this wind simulation in relatively homogeneous condition, then we let the flow adjust to the real map. So a few basics about the turbulence in canopy. So typically there are, of course, all the atmospheric turbulence, but near the ground, and so near the flame, especially when you are with a tree canopy. There is some shear, strong shear near the surface, because the flow has a low velocity inside the canopy and a high velocity above it. And this shear produces some large coherent structure that can be estimated in terms of size and duration. And typically it depends on the height of the canopy. So if you take the example of a 20-meter high canopy, then the correlation distance, the correlation time will be around 10 seconds. And of course, if you take a very short grassland, then it will be much smaller than that. So it will be less amount of turbulence that will probably play a lower role on the fire. But when you are in canopy fire, or when you have a big canopy, it can affect the turbulence. And the distance between these coherent eddies can also be estimated from numerical experiment, empirical experiment that has been done to estimate this factor here. And so they are typically on the order of 50 and 100 meters. So this coherent structure is what you can see when you look at a field of wheat or corn or anything. And you can see them in this case because the vegetation is flexible, but there is the same kind of stuff in forest canopy, and when you are below, you can feel the intermittence. About 50% of the energy is released during only 10% of the time. So the model can explicitly account for this, and there is a version of MesoNH that also works like that. Interestingly, one of our co-authors on this paper is also a co-author of the paper of the guy who did the MesoNH version, which is Sylvain Dupont from INRAE in Bordeaux. So there is a drag term, volumic drag term, and the turbulent kinetic energy produce some shear related to this drag and the difference of velocities. So there is a dissipation which has a slightly different coefficient when you are in the vegetation. There is a production with the shear, the dissipation, and there is also the wake that induce transfer to the smaller scale. So what you can see on this figure, on this animation, which I will maybe start again, is a top view of a homogeneous forest. So the trees are not represented here, but there are some trees, and in the break that is in the middle, there are a few trees. So you can see this coherent structure and how the wind accelerates in the break. There are some empirical data that has been captured in the field or in soufflerie, le mot m'échappe. Wind tunnel, thank you. Wind tunnel, and so there have been some measurement of different profile and also the amount of turbulence statistics. So these data can be used to evaluate the model and to set up the drag coefficient. It's always difficult to have a good idea of what is the drag coefficient because there are some very fine measurement at the scale of the leaf, but it's different coefficients that should be used at larger scale. So when you use this cyclic boundary condition, you have you correctly develop this turbulent structure due to the shear, but there is the flow will tend to decrease in velocity because of the drag near the soil. So you need to have a forcing to maintain the flow over time, and there are typically two different approaches for that. Classical different approach. One is what is used for the large scale, and this is typically what is used in MesoNH, which is based on the Ekman balance. So there is a pressure gradient due to the geostrophic wind here, and there is the Coriolis force. So this Ekman balance results in wind profiles that are stable over time. But the Ekman balance also induced the spiraling of the wind due to the Coriolis force, so that the wind is tilted from the pressure gradient as long as you go near the ground. And so there are two practical limitations to that when you want to deal with wildfire. The first one is that you prescribe the geostrophic wind at the top, which is very different from what you expect at ground level, and so you cannot really force the exact value that you want. And also the fact that because of the rotation, you have some shift in direction, and so it's even complicated to prescribe a direction. So some other approach have been used at a small scale, typically to work on canopy flow, typically with low domain. But it turns out that so it simply assumes that the pressure gradient is constant and neglect the Coriolis force. It turns out that when you apply this kind of method to a high domain, which is required when you want to do forest fire, to correctly simulate your plume, you have some profile like that. So the wind tends to decay over time with this crazy S shape. And so it is not a good solution too, because you have an unrealistic profile and you also have a slow convergence when the domain is high. Another aspect of this forcing is that the Ekman balance typically creates these large structures that are rotated due to the Coriolis forcing again. So you have more or less the same kind of structure when you do the pressure gradient. Visually, they look relatively identical. But when you average over 1 hour, these streaks here are intermittent, so they tend to disappear when you average. Whereas with the pressure gradient constant, your streak is locked. And so, because there is no mechanism we are in cyclic boundary condition, so when the wind is fast here, it's again fast here, and there is no mechanism to reduce this, the formation of these local streaks. So this is something that has been observed with other models, which is why typically at large scale this is the approach that is used. Another critical question is the question of size and resolution. So here these are some spectra that are computed for different domain. So this one is a 3-kilometer domain with the Ekman balance. So it's a typical atmospheric simulation, let's say. So we have this black spectrum. And what we see is that if you go to a finer resolution with here in that line, then you have more small scale turbulence. And of course, this is not modeled when you use the too large grid. And typically, depending on the vegetation and the size of your vegetation, this turbulence can matter for your fire. So, and also we want a smaller domain to reduce the computational cost. So typically, we would be tempted to use domain like that. So we see that we have some of the large scale and the fine scale are appropriate. But if you go to the constant pressure gradient and small domain, then it becomes to be something ridiculous with large scales that are incorrect. So facing this problem, over time with FIRETEC, we developed a methodology that was only recently published, but that has been used for 80% of LANL simulation of FIRETEC over the last decade. So it is based on the modification of the Coriolis force to make a pressure gradient that is aligned with the wind direction so that we don't have to deal with the rotation problem. And this forcing also allows to specify a velocity at a given height, but at the same time, it doesn't produce some streaks, locked streaks. So the idea is that first, if you take a constant pressure gradient, you have too much forcing to the top, because in reality, if you do a projection of the resultant of the pressure gradient and the Coriolis force on the wind direction, you can see that the effect on the mean flow is something related to the rotation. And so if you draw the angle associated to the rotation, this coefficient goes to 0 when you are close to the top of the domain, which is why the wind is stuck to the geostrophic wind. And when you decrease, this forcing increase, so that you have forcing near the ground that maintain your flow. So the idea is that instead of using a constant pressure gradient, you can use this profile first. And the other idea is that if you look at the Ekman balance, you can demonstrate that this Ekman balance is stable, meaning that if you have some velocity that is higher than the mean profile, it will take it back to the original value, meaning this balance is stable. And in this sense, it acts to destroy the streaks. So our interpretation was that this mechanism was responsible for the appearance and disappear of the different streaks. And so the idea of this new setup was to combine this profile so that we have no rotation. So we use a forcing derived from the Ekman spiral assumption. We did the forcing based on mass flow so that the mass flow is conserved at a given height. So it was a way to force the wind at a given height instead at the top of the domain. And the last idea was to have a force to move back the velocity when the departure to the initial profile is large. And this forcing was dimensioned according to the characteristic time derived for the Coriolis force. And so we did some simulation of this forcing to compare with the Ekman balance. I will not show all the detail, but this is in the paper. So the first thing is that you still keep the streaks, but they are intermittent at the right scale, and that the spectra are okay. So the idea is that using this forcing, you can have all the desired aspect of what you want for theoretical study, in which you don't want to have a spiraling wind and to set up the wind from the top. So this was what was used in the FireFlux experiment simulation to generate the precursor wind flow. And then these values were applied to the side of the domain to generate as a boundary condition so that the wind flow can develop inside the domain according to the real vegetation that was set and the drag coefficient. So we had this region here where there are some tree, we have the tree block here. And so this is an example of average wind over 5 minutes, where you can see here that the wind is faster in this corridor, and it tends to increase. Whereas here you are in the leeward side of the block. And so the interest of this was that we were able to have different wind profile at the two different towers. I don't show the detail because it has been described before, but in this setup we obtained slower values for the wind that was near the canopy. When you compare the fluctuations that was observed and what we pre-compute, we see that the magnitude is not as high. So we are missing all the large scales that are caused by atmospheric factors that are not represented in these simulations. And we will see later the impact of this. So these are the fire simulations that were done. So Jean-Luc found that the spread rate was highly sensitive to the ignition timing. So at that time, it was some time ago, we didn't do ensemble simulation as done by so yeah, ensemble simulation were used here and here in a more recent paper. And these are different contours. Okay, so Jean-Luc selects some points that were reasonable in times about the arrival time. And what we showed was that there are large variation among the signal at the different location, and a lot of variability among the variables. So it makes a sense to do the ensemble simulations that Aurélien did. And the other aspect was that because it was only point measurement, the fact that comparing details of this simulation was probably pointless, but that comparing the general trend was more interesting. So this is the results that were obtained for the vertical velocities at the different height. So in black the simulation, in red the experiment. So of course all the details are not exactly the same, but the magnitude of these fluctuations, those that were really created by the fire, are on the same order. We can see some details like the downdraft that were correctly captured. If we look at the temperature, we can see the same stuff that Aurélien just showed before. The fact that we had more higher temperature before the fire arrived. So the interpretation of Jean-Luc at that time was probably that depending on the exact wind field, the heat released by the ignition arrived or not to the tower. And so apparently in the simulation, in the experiment, it was not the case. But in our simulation and the previous one, it was the case. We can find also the wind speed increase. I will not spend a lot of time on this. And the final stuff is the spectra. The spectra was computed at the point of the measurement, so it was compared to the observation. So the scale is reversed; it's a scale on time. These are the large scale. So in colors, it's 3 different points in the streamwise direction. And so what you can see is that these fluctuations that are created by the fire are correctly captured. Regarding the large scale, as I said, and we can already see it in the wind field, we don't have this large scale. The question is, even we can theoretically reproduce this large scale, because we will not be able to reproduce exactly the same large-scale structures than in the experiment. How can this be integrated in such an experiment? And just a final point, some details matter. In the first run, Jean-Luc didn't do any clearing near the tower, and he found very high temperature because the fire goes just under the tower. And when he did a little bit of clearing, we had better results at the 2-meter tower. So I don't think these conclusions that were for the last presentation are very relevant here. I will just say a few words about another application of this ability of this kind of model to simulate wind. One of the big questions is to know if the winds that are captured are representative of what's going on in fire experiments. So you have your measured wind here with a sensor, and you have the idea is that above the canopy, the wind velocity will be the same, just shifted from the top of the canopy, which is that this hypothesis is at the basis of most of the empirical models that are done in the field. So the interest of a model like FIRETEC is that you can explicitly simulate the difference between what is measured here and what is seen here. So typically, if you do a profile, an horizontal profile of the wind velocity at the height of the tower, you see that the velocity is low inside the canopy. It progressively increases as you go far from the edge until reaching more or less a maximum, and it decreases again in this zone. So for sure, it's not homogeneous here, and the distance to adjust is very long. Typically here we are at 7 times the height of the canopy. So if your canopy is 20 meters, it's 100 meters and 40. And there are some evidence in experiments that it can go until 30 times the height of the canopy, which is really, really big. When there is a transition from cleaning to forest, it's in general faster, as seen here. Typically, an equilibrium is reached after 10 times the height of the canopy, and most of the changes are done here. And we can see that even above the canopy, at 10 meters above the canopy, the wind is not constant. Here, the wind increases above near the leading edge of the next block. So in many experiments, we don't know the exact position of the tower, which if you think about the Fermi experiments, for example, or this kind of experiments, sometimes it's very far. So it means that there is potentially this systematic bias due to the location of the tower from the edge. And there is another source of bias, which is that, of course, the wind has some fluctuations. If you look at instantaneous correlation between 2 points that are more than 2h, there is no instantaneous correlation between the wind velocity. the wind velocity are correlated at distance only if you start to average over time. And typically the duration of fire experiments is in general short, with the time required for a convergence. And so we did a study some time ago about how the measurement can be improved by increasing the number of sensors, increasing the dimension of experimental plots and the duration of experiment. But if you combine this systematic bias and the random errors that are due to the experiment setting, you can see that between the measured wind and the fire wind, this is typically the plot you obtain. So there is about 30% of error in most of the, let's say, old style experiment with a single tower, which is on the amount of the error of the empirical model, so it's probably related to uncertainty of wind too. Another aspect is that we can compute correction coefficient to see how this error is reduced by increasing the number of sensors. So of course this work has not been done with LiDAR data of wind, but it would be interesting to look at that too. And the last point is that yes, we can reduce this error by increasing the number of sensors, which I just said before. Thank you for your attention. Here are a few references to the papers that were listed in this talk.